So, very good evening to all. This is live discussion session number 5 for the course entitled Basic Thermodynamics, Classical and Statistical Approaches. And this is the course code is NOC24CY04. And myself, Akash Gutal. I'm PhD student in the Department of Chemistry, Indian Institute of Technology, Jodhpur. So, first, before starting the problems, we will do some revision from the last week classes. So I will start from the second law of thermodynamics. So the second law of thermodynamics actually introduce the concept of entropy. And before, so the general statement of the second law of thermodynamics is the entropy of system and surrounding always increases. Or we can say the system entropy plus surrounding entropy is always greater than zero. So we can say the universe entropy of universe al always greater than. So the entropy of universe always increases. So to define the meaning of entropy, we went to Carnot cycle. So first I will define what is the Carnot cycle. So Carnot give this the most efficient cycle to construct an engine. So this Carnot cycle actually having four different processes in it. The first process is isothermal expansion. The second process is adiabatic expansion. The third process is isothermal compression. And this is expansion, compression. And fourth process is adiabatic compression. And Carnot cycle is the most efficient cycle. And and this the efficiency of the Carnot cycle can be given as eta is equal to the total heat. Uh, so the efficiency can be defined the total work done by by the engine, which is nothing but so Q1 minus Q2 divided by Q1. Suppose this is the heat getting inside is Q1 and heat is thrown away from the third cycle is Q2. Then the difference between them is the work done by the system, and the total heat gained by the system is Q1. So this will give you, so by sign convention you can put plus also. So this will be Q2 by Q1. So when you put proper sign, it will be comes eta value will come less than 1, and it can also be written as, suppose, uh, let's say this is the temperature T2 and this is T1. So the efficiency can also be defined as 1 minus T2 by T1. So the efficiency, we, we can say efficiency, maximum efficiency can go up to 1, but ideally, but it is ideal condition. This is not possible. So we'll add one slide. Then we defined the entropy using the Carnot cycle, and the definition of entropy. So there is one statement regarding the efficiency of a uh, efficiency of the engine, which is also can be considered as the statement for the second law of thermodynamics. So that statement goes like this: one cannot make an engine with efficiency so 1. Okay, so one cannot make engine with efficiency 1. So this is not possible. And the definition of entropy we get from Carnot cycle is, it is the heat exchanged by the system in the reversible process at temperature, so at temperature T. At temperature T is nothing but entropy. And we know that entropy is a state function. So entropy is thermodynamic state function. And at the end, um, one can, so at the end, I would like to tell there is Clausius statement, which is important for today's problem. So the Clausius statement says that heat flow, Clausius statement says that the spontaneous flow of heat from cool body to hot body is never possible. spontaneously never possible. So this is the Clausius technique. So the spontaneous process will be the transfer of heat from hot body to cold body, but it is never be the heat transfer from cold body to hot body. It will never happen. So this is termed as Clausius technique. This is given by the Clausius. So we'll go towards our problems. So the first problem is here. So problem goes like this. Calculate the work done on the cyclic process shown below. So the PV diagram is given and the four options are given. So I'm giving you some time, 3-4 minutes. You can solve, and if you are getting the answer, you can put it into chat box. So you can work out this problem. You can pause the video and then work out and see the solution. So the given things here are the Q and the heat getting inside the system. This is the system like given like a Carnot cycle. So the input Q, the heat input is 600 joules. At the hot temperature is 600 Kelvin. And the Q2 you need to Q2 is not given, but the T lower temperature is given 400 Kelvin. So we need to find out what is the work done in the cyclic process. So the work done is actually nothing but the difference between the heat gained by the system and the heat released by the system. Whatever the according to the first law, it should be converted into the work. This problem can be solved by the efficiency equation also. So we will work out the problem. Q1 is given 600 joules and T higher temperature is at 600 Kelvin and T lower temperature is 400 Kelvin. So what we know about efficiency? Efficiency is nothing but 1 minus lower temperature divided by higher temperature. Okay? So we can calculate the efficiency. 1 minus TL is 400 divided by T higher is 600, which gives you 1 minus 2 by 3, which is nothing but 3 by 3 minus 2 by 3 is 1 by 3. The efficiency is 1 by 3. So we know the another definition of efficiency is nothing but the difference between the work done divided by the heat gained by the system. Fine. So this work done can be defined as the difference between Q2 and Q1, which is nothing but Q1 minus Q2 divided by Q1. So this will give you 1 minus Q2 by Q1. And so this we have 1 by 3. So this will be the same. 1 minus 1 by 3 is nothing but minus 2 by 3. And Q2 by Q1 is also 2 by 3. Fine. So we know the relation that Q2 by Q1 is nothing but the T2 by T1 is nothing but in this case, this is TL by TH. Right? So Q2 by Q1 is 2 by 3. Hence, so I'll continue this side. So we need to calculate Q2, which is 2 by 3 into 600, which is 400 joules. And we know the work done is nothing but Q1 minus Q2. So the work done is equal to Q1 minus Q2. It's nothing but 600 minus 400, which gives way to 200 joules. Right? The answer is option number first. So here is the next second question. So the question goes like this: calculate the total change in the entropy for the process shown below. So there is a diagram of T and V diagram, T versus V diagram, and the cyclic process is given. We need to find out total change in the entropy. So I'm giving you the two minutes to solve this question. If you require longer time, you can pause this video, do the calculation, and check the answer. So in this problem, they have given a TV diagram, and A, B, C process is given. And as we can see, this is a uh, triangular graph is actually shown, which is cyclic in nature. Once it is cyclic in nature, you are asked about the state function. So we know that second law of thermodynamics that the S, that is the entropy, is a state function. So for any cyclic process, the entropy change will be zero. So this is cyclic process where it is going and it's arriving at the same point. So we can say its entropy change should be zero. So the correct option is option number B. So the next question is question number 3. Is a Carnot engine getting heat at 800 Kelvin is used to drive a Carnot refrigerator, maintaining 280 Kelvin temperature. Both the engine and the refrigerator rejects heat at the same temperature T when heat given to engine is equal to heat absorbed by refrigerator. Determine efficiency of engine. So please try to solve this problem. Take 2-3 minutes to uh, analyze and solve the problem. So here is a system in which uh, we are having a Carnot engine, which is having its uh, high temperature, or we can say a hot bath is at 800 Kelvin. And whatever the work that this engine does, it used for refrigerator, which is having its own uh, separate bath, cold bath, which is actually nearly 280 uh, Kelvin temperature. And both the engine and refrigerator, is giving rejecting the heat to the uh, same temperature T bath. There is a common bath where these two, refrigerator and heat engine, is rejecting the heat. So and there is one statement is given. Next statement is when heat given to engine is equal to heat absorbed by refrigerant. So whatever the heat engine is getting the heat to do work is actually the same heat is getting by uh, uh, that refrigerator from 280 Kelvin temperature bath. So this information is given. We need to find out what is the efficiency of given engine. So we'll start drawing the uh, given things. So it will be better to understand by drawing the diagram. So here is the 800 Kelvin heat bath of engine. And here suppose this is 280 Kelvin cold bath of uh, refrigerator. So, and there is at the end we know the common they are rejecting heat to the common heat bath which is at, let's say, T. They have given T Kelvin temperature, and suppose this is the engine taking Q amount of heat and rejecting Q engine, uh, and this is doing work which is used to run the refrigerator. So let's draw a reference type R, and which is getting heat, the same heat. Q is R is getting taking out the same heat from 280 Kelvin bath, which is Q, and it is rejecting heat to the same bath at temperature T, which we call Q. This is for R. Right? This is the work. So we have three things similar. First is the temperature of the bath to which both the systems are rejecting the heat, work done by the engine and work done on the refrigerator. And third thing is we have same heat absorbance from both the engine and refrigerator from their respective hot and cold baths. So these three things we need to use to solve this problem. So first step would be we must we have to calculate the efficiency eta for engine, which we can write it as, according to the definition, we know it's nothing but the work done by heat get supplied to the engine, which is W by Q. And there is another way we can write it in terms of temperature is 1 minus T cold divided by T hot. But we know what is the T cold for engine is T, and T hot is nothing but 800 Kelvin. So we'll simply write T divided by 800. That is, yeah. So we in this equation, if you write see in equation 1 and equation 2, if you see carefully, we have three things which actually are common. So that will help us in getting things simplified. So W, Q, and T are both common to refrigerator and engine. So what we can do, we can equalize these two things because the left hand side is the same. So we can equalize this. So we know we get W by Q is equal to 1 minus T by 100. Right? Uh, the main goal is we need to calculate T and put in this equation, we will get the answer. Okay. This is our main equation. So this is our important equation. Fine. This is our important equation. We need to find out the temperature of the baths to which these two engine and refrigerator are rejecting the heat. So let's describe. So keep this equation in mind. Let's say equation number 3. Similarly, we can write the similar equation in case of refrigerator. But you all know in the for the refrigerator we are not having efficiency. We are having coefficient of coefficient of performance. This coefficient of performance can be given as beta is equal to the heat taken from cold reservoir divided by work done on the refrigerator. So as we know that heat taken from the cold reservoir is Q. So we will replace this by Q by W. Fine. So this is in terms of heat and work. So another equation we can write as beta is equal to QC can be written as in terms of because it directly proportional to temperature TC divided by and work is nothing but QR minus Q, and we can say that it is temperature T minus which is proportional to the temperature T, and Q means the temperature of cold reservoir. Right? So this will give us these two equation 1 and 2. In similar way, we are also here getting first we put the values 280 T minus 280. Fine. Let's say this as equation. So as you can see, here also we are getting the Q by W, and here also we are getting the beta coefficient of performance term uh, coefficient of performance in terms of the temperature of rejecting bath T. So again we can equalize 1 and 2 to get Q by W. Q by W is equal to 280 divided by T minus 280. So here we are having W by Q. So let's convert it by in W by Q for simplicity to comparison. So this will be T minus 280 divided by 280. So we are getting the both things. And fourth equation. So we can easily compare these two. W by Q is the same. W is same and Q is the same. So W by Q for in both the cases will be the same. So we can equate this by equating 3 and 4. We will get, sorry, this will be, sorry. I should give the different numbers 4, 5, sorry. 6. We should equate 6, 3 and 6. So we will get 1 minus T by 800 is equal to T minus 280 divided by 280. Fine. So we can write it 800 minus T, 800 minus T divided by 800 is equal to, so for that is equal to T minus 280 upon 280. T minus 280 upon 280. And so we need to find out what is the value of T. So I think it is better to divide and then subtract. 800 T minus 280 divided by T by 280 divided by T by 280 minus 1. Okay. If you transfer this minus 1, it become plus 1. You transfer this to this side. So you will get 2 is equal to T by 280 plus T by 800. So we can do the method algebra. 2 is equal to 280 plus 800 into T divided by 280 into 800. So for T expression we will get 280 into 800 into 2 divided by 280 plus 800. Please, please calculate the T temperature for the bath to which these two systems are rejecting the heat. 280 cos 800 cos 2 divided by 80 plus 800. So 80 plus 800 is nothing but 800,008. Sorry, 8 and 10 8. We calculate it. If you calculate the same or so that this will come out to be 412.61 Kelvin. So logically, if you say this engine is having heat bath at 800 Kelvin, which means it will reject to the system to which having less temperature than this heat bath. And similarly, in case of refrigerator, the 280 Kelvin is a cold bath, and the refrigerator must be rejecting the heat to the reservoir, which is having temperature greater than 280. So this temperature must be in between 800 to 280. And we are getting the same 412.61. So now we need to calculate eta value. That's the efficiency. The efficiency that we having, engine efficiency is 1 minus T by 800. So we know that T is equal to 412.61 by 800. Please calculate it. So if you calculate it, it comes out nearly 0.48. So the efficiency that we get is 0.48. The option number B. So question number 4. Let's say a system is going from state 1 to state 2 through two paths at a fixed temperature T. One is the reversible path and the other is an irreversible path. Which of the following statement is right? Correct. Entropy change of system is same for both the paths. Entropy change is more in irreversible path. Entropy change is more in the reversible path in none of the. So take 2-3 minutes to solve this problem. So this question is about PV diagram is given, and there are two paths. One is the reversible path, another is the irreversible path. And the heat changes are given del Q and del Q R. So we have been asked that correct statement. The first statement, entropy change of the system is same for both the paths. For the system, the entropy change of the system is same for both the paths. As the S is state function, both paths are going towards the uh, same going towards the same state, state two. Because of that, we can say in the system point of view, the entropy change is zero, or zero in the sense for both. Sorry, not zero. It's a entropy change for both the paths are the same because they are ending to the same state. Because of that, the entropy change of the system is same for both the paths. Volume. So you'll find that at increasing temperature, the pressure is also increasing, which means the graph between the temperature, uh, as the temperature at the temperature as the temperature increasing, the pressure also increases. So P1, P2, P3 are P, P3 as we can see, or T1, T2, T3. These are the P1, P2, P3. So the graph, it should be, so we can associate this that the P3 is higher and P1 is lower. As we know that P is directly proportional to T. And what with the entropy, as P3 is increasing, P1, P2, P3. So the P1 is for, as you can see, the P1 is lower here, and we find this curve P1 is lower, P2 is middle, and P3 is higher. So that's why. And for adiabatic also, we know that entropy is constant. Because of that, the second option is correct. So the question number 6. Some heat engine A and a reversible heat engine B operate between same two heat reservoirs. Engine A has the thermal efficiency equal to two-thirds of the reversible engine B. Which of the following sentence is right? Engine A is an irreversible engine. Both engines are reversible engines. One is more efficient and other is less efficient. None of them. So take 2 minutes to solve this problem. So in this problem, the some heat engine A and the reversible heat engine B uh, operate between same two heat reservoirs. So they have given that there is engine A and engine B operating at same reservoir. So they have given that engine A has the thermal efficiency equal to two-thirds of that of the reversible engine B. A engine has efficiency efficiency of A engine is two-thirds of the efficiency of B engine. And which of the following statement is right? Engine A is an irreversible engine. Both engines are reversible engine. One is more efficient and other is less efficient. None of them. So the answer should be A. engine A is an irreversible engine. Why? Because we know that the maximum efficiency can be achieved only using the reversible heat engine, and uh, there will not be any other type of engine which can operating between these two temperature, which can give us more efficiency than the reversible. So taking that statement from the second law of thermodynamics, the engine A is an irreversible engine is the right answer. It should be the irreversible engine because its efficiency is less than the reversible engine. Question number 7 is identify the corresponding PS diagram for PV diagram given below. So there is PV diagram is given. You need to find out what exact representation of the system using TS diagram. That is the temperature entropy diagram. Take 2 minutes to solve this question. So in this problem, you can see the PV diagram is given. So the PV diagram 2 to 3 process is seems like adiabatic process, and or we can say it's a expansion, and 3 to 1 is process in which the pressure is constant, isobaric process, and 1 to 2 is again uh, there is compression. And we can see 2 to 3, the expansion is happening. We know when the volume is increased, the entropy will increase. And we need to find out where the for 2 to 3 process, the entropy is increasing. The option 1 and 2, in which 2 to 3, the entropy is increasing. The second part is 3 to 1 isobaric process. The compression is happening, which means the entropy must decrease. 3 to 1, the entropy must decrease. But in first diagram, the 3 to 1 entropy is decreasing, but in second diagram, 3 to 1 entropy is the same. So for compression, entropy must decrease because the volume is increasing. And because of that, if you find for 1 to 2 process, the same thing as it is, as we can see, the compression is happening, but the entropy is constant. This is because it must be the isothermal process. Uh, Sorry, it is not it's adiabatic process. Okay, sorry, it should be the adiabatic process. 1 to 2 is adiabatic process, and 2 to 3, as we can see, the entropy is increasing, and the curve is like uh, isothermal. So hence we can say that the option 1 is correct. For the processes 1 to 2, it's like the entropy is constant, means it is adiabatic process. The next question is, the figure below represents a simplified PV diagram of the Joule's ideal gas cycle. All processes are quasi-static and Cp is constant. What will be the thermal efficiency of the engine performing this cycle? So there is a PV diagram of some cyclic process is given. We need to find out the answer. Please take time to solve this question. So we will solve this problem. So I will take, will add one slide. Let me add one slide. Yeah. So we are having a PV diagram with, let me copy this. This is the PV diagram. Uh, so what we can see here, the process 2 to 3, P2 pressure is constant. It's isobaric process and the volume is increasing. And 3 to 4 is adiabatic and adiabatic expansion. 4 to 1 is again isobaric compression and 1 to 2 is adiabatic compression. So the heat is getting inside the system from two channels, from one channel, which is process 2 to 3. Isobaric process, the heat is getting inside, and as you can see, and from process 4 to 1, in the compression process, the heat is getting out. So let's call it as Q C, Q in versus Q out. So what we have, we know Cp is constant, and we know that heat Y we can calculate, which is nothing but Cp into integration of Cp T2 to T3 dt, which is nothing but Cp T3 minus T2, fine. And Q out is nothing but integration of T4 to T1 from Cp dt is equal to Cp T4 minus T1. So this is the Q in and Q out. And we know the efficiency of the engine is nothing but 1 minus Q uh, out divided by Q in, and we will be having 1 minus Cp. We know that T3 Cp Qo is C4 minus T4 minus T1, T4 minus T1 divided by Cp T3 minus T2. Okay. And when one can uh, delete this Cp because uh, Cp is a constant, is given in the problem. So efficiency will turn out to be that is equal to 1 minus T4 minus T1 divided by T3 minus T2. Right? But as we know, there is a relation between T3 and T4. Similarly, T2 and T1 because they are connected to adiabatic processes. Adiabatic process, we can relate the P2 a P1 and T1 T2. Similarly, P2 P1 and T3 T4 using uh, adiabatic relationship between P and T. We know this relationship is P versus T is P T is gamma upon 1 minus gamma is constant. So we can calculate, we can say in case of first case, it's calculated between P2, P1, T2, T1. So P1 upon, so we know that for P2 in P2, so, so P2, T1, uh, sorry, it's T2, P2, T2 raised to gamma minus 1 minus gamma is equal to P1, T1 raised to gamma upon 1 minus gamma. From that, we can calculate P1 by P2 or the relation between T2 and T1. So we will get it T2 divided by T1 is equal to, we can transfer P1 by P2 raised to 1 minus gamma upon gamma. So this will be the relation between T2 and T1. Similarly, we can get the same relation for T3 and T4. For T3 and T4 is to calculate P2. Again, we will write P2 T3 raised to gamma upon 1 minus gamma is equal to P1 T4 gamma upon 1 minus gamma. P1 T. Yeah. And similarly, we can get the relation between these two. It's T3 divided by T4 is equal to P1 by P2 plus 1 minus gamma upon gamma. And can get this. Uh, I think it should be gamma minus 1. I think PV relation is to gamma is constant. PV is equal to nRT, which is gives rise to V is equal to T by P. So T by P, if you get then 1 minus gamma. Yeah, right. 1 minus gamma. So, sorry. So again, we need to calculate T4 and T1 in terms of, so we need to put this relations in this efficiency equation. Let me check again the relation. So gamma upon 1 minus gamma is right. 1 minus gamma is right. So we need to put it into eta is equal to 1 minus T4. Let's calculate. We can say T2 is equal to P1 by P2 raised to 1 minus gamma upon gamma into T1, and T4 is equal to T3 is equal to P1 by P2 1 minus gamma upon gamma uh, into T4. So we put this two in equation, above equation, we'll get eta is equal to 1 minus, let's put T2 and T3, 1 minus T4 minus T1, and T3 is P1 by P2 raised to 1 minus gamma upon gamma into T4, and minus T2 is nothing but P1 by P2, sorry, P1 by P2 raised to 1 by P2 raised to 1 minus gamma upon gamma and into T1, and that gives you 1 minus, if you take out this P1 by P2, 1 minus gamma upon gamma common, then you will find T4 minus T1, P1 by P2 raised to 1 minus gamma upon gamma into T4 minus T1. So that will cancel out, T4 minus T1 will cancel out. And we will get the efficiency, we'll get the efficiency as eta is equal to 1 minus P1, 1 minus gamma, if you take it upwards, uh, it in numerator, we can change the sign of 1 minus gamma, which is nothing but P1 by P2 raised to gamma minus 1 upon gamma. This will be the answer. So answer will be 1 minus P1 by P2 gamma minus 1 by gamma. The answer is option number A. The question number 9 is, according to the Clausius theorem, which of the following is correct? So the Clausius theorem is given that which of the following is correct? So for cyclic process, it is asked that cyclic process work done constant temperature, not constant temperature, work done by the given temperature is equal to zero. Or first option is that. Second option is enthalpy constant at given temperature divided by given temperature is zero. The heat is divided by temperature is zero, or the internal energy divided by temperature is zero. So this is related to definition of entropy. So we know that how we define the entropy is nothing but reversible heat absorbed by the system at divided by the temperature is the entropy, change in entropy. And we know by the definition of entropy that cyclic integral of Q at divided by temperature is zero, because S is a state function. Answer should be C. So this is the Clausius theorem. Question number 10. So the question number 10 is, an inventor claims to have developed an engine that takes in 100 millijoule at temperature of 400 Kelvin and rejects 40 millijoule at temperature of 200 Kelvin while delivering 15 kilowatt hour of mechanical work. Check whether the engine is feasible or not. So first we will take out the given things. The engine takes heat uh, heat taken is 100 millijoule at 400 Kelvin and heat rejected is 40 millijoule at 200 Kelvin. Fine. And the person is claiming that given engine can produce work 50 kilowatt hour. So we'll convert it into joules, that is 15 into kilo is 1000 into watt is nothing but joule per second, and hour we can convert into second as 300 and 3600 seconds, which gives you 5.15 into 1000 into 3600. It's 5.4 into 10 raised to 7 joule. Well, and according to the engine work done is Q taken minus Q rejected. It's nothing but 100 minus 40 millijoule which is nothing but 60 millijoule. And this is nothing but 60 into 10 raised to minus 3 joule. So 0.012306 joule. So this work, maximum 0.06 joule work can be done by this system. If you calculate the efficiency, is 1 minus 5.4 to 10 raised to 7 joule divided by uh, the heat taken, which is 100 into 10 raised to minus 3 joule, which gives you 1 minus, sorry, uh, sorry. Even if you don't calculate the efficiency, the maximum work can be done by this type of engine is 0.06 joule. But actual work is, the person is claiming that it can calculate 5.4 into 10 to 7 joule, which is a big number, which is actually violates the second law of thermodynamics, which is, the answer should be first option.